You can classify numbers using sets. A set is a well-defined collection of objects. Each object is called an element of the set. A subset of a set consists of elements from the given set. You can list the elements of a set within braces. A rational number is any number that you can write in the form a over b, where a and b are integers and b does not equal 0. Each graph below, or on the next slide, shows a subset of the rational numbers on a number line. So first we begin with the natural numbers at the top. The natural numbers, review from a previous lesson, 1, 2, 3, and so on, following that pattern in the positive direction. We can see those represented here on a number line with points at 1, 2, and 3, and of course so on. The whole numbers are almost identical to the natural numbers, but they include one more element, and that's 0. 0 kind of looks like a hole, so if you're looking for a way to remember the difference between the natural numbers and the whole numbers contain that element that looks like a hole. So 0, 1, 2, 3, and so on in that direction. We can see those graphed at the right. And then the integers. The integers are all of the whole numbers as well as all their opposites in the negative direction. And we can see those graphed on the number line at the right. An irrational number cannot be represented as the quotient of two integers. So it cannot be represented as a over b, where a and b are both integers and b is not 0. On the left, we see some information regarding rational numbers. On the right, irrational numbers. A definition: rational number, a real number that can be written as a ratio of two integers. Rational numbers in decimal form are either terminating or repeating. So terminating means they end, they don't go on forever. Or repeating, if they do go on forever, they follow a pattern and begin repeating. So some examples: a terminating decimal, 5.45, and a repeating decimal, 0.41666 continually, or 0.416 with the bar over the top to represent the 6 repeats indefinitely. All right, below that, if a whole number is a perfect square, its square root is rational. For example, the square root of 4. We know 4 is a perfect square. The square root of 4 is equal to 2. Another example, the square root of 25, a perfect square, equals 5, a rational number. Moving on to irrational numbers on the right. An irrational number is a number that cannot be written as a ratio of two integers. Irrational numbers in decimal form are non-terminating and non-repeating. Some examples: 0.10100100001, and so on. And pi, 3.14159.265, and so on. Both of these, when written in decimal form, are non-terminating, so they go on forever, and also non-repeating. Even though the first one seems to have some sort of pattern going on, it's not repeating itself like it would if it were 0.101010. It's a different pattern. If a whole number is not a perfect square, its square root is irrational. An example: the square root of 3. Note that 3 is not a perfect square, and its square root, approximately equal to 1.732058080, is irrational. Second, the square root of 10. 10 is also not a perfect square, and so its square root, seen here as 3.16227766 and so on, is irrational. Rational numbers and irrational numbers form the set of real numbers. So when we put these two sets together and combine all of their elements into one set, we call that set the real numbers. Problem 3, classifying real numbers. To which subsets of the real numbers does each number belong? Part A, 15. We'll start with the smallest set, the natural numbers, and we'll check. Is it a natural number? Well, if you remember, the natural numbers are 1, 2, 3, 4, and so on. And yeah, it's a natural number. Then we move to the next larger set, the whole numbers. Now, because it's a natural number, it's also going to be a whole number. The natural numbers are considered a subset of the whole numbers. That means that every single natural number is also a whole number. So because it's natural, we don't really even need to check anymore whether it's a whole number. We know that it's going to be because it's a natural number. So the whole numbers. The whole numbers are a subset of the integers, as we saw earlier, and then the integers are a subset of the rational numbers. A little bit further on that point, 15 can be written as a fraction. It can be written as 15 over 1, and both 15 and 1 are integers, so by our definition of rational numbers, it is a rational number. So once more, 15 is a natural number, a whole number, an integer, and a rational number. Part B, a number in decimal form, negative 1.4583. Well, we can first check, is it a natural number? No, it's not in the set that begins 1, 2, 3, and so on. It's also not a whole number, because it's not in the set that begins 0, 1, 2, 3, and so on. It's not an integer, because it's not a whole number or its opposite. But it is a rational number. Notice it's terminating. It doesn't go on forever. And since negative 1.4583 is a terminating decimal, we can say that it's a rational number. Part C, the square root of 57. So a moment ago we saw that anytime we have a radicand that's not a perfect square, that number will be irrational. So we can state the square root of 57 is an irrational number since 57 is not a perfect square. Your turn. Part A. To which subsets of the real numbers does the number the square root of 9 belong? Part B. To which subsets of the real numbers does the number 3/10 belong? Part C. How about the number negative 0.45? And D. The square root of 12.